How's it going, AS Math? It is Mr. Knight here, back again, continuing on with calculus, and I am featuring my 8th hour today.
Nice.
They're stoked. All right. So double derivatives. Let's talk about those guys for a little bit. Okay. So what I've alluded to this whole time is that functions can actually be differentiated more than once, right? So if I have my original function, you could see it as f of x or y equals. If I take my first derivative, we call this f prime of x or dy dx. And then if I do the second derivative, it's f double prime of x. And this is kind of how we do the dy dx. It's really wonky, and it looks like we're squaring this thing, but we're not doing that. It's just represented as the double derivative of y with respect to x twice. Okay, and taking the double derivative is just like taking the derivative of the derivative. That's all it is, right? So just give an example right here. If I have a function y equals x to the fifth plus 2x, I want to find the double derivative of this guy. So I'll take the first derivative using my power rule. Again, I'm taking this number, moving out in front, multiplying it, and then I have to subtract 1 off that, right? So I get 5x to the fourth, and I can do the same thing and just get 2. To get the double derivative, I'm just going to take the derivative of that guy now, using the same exact power rule that I just mentioned. 5 times 4 is 20, and now it's x to the third power, and the 2 just goes away. Okay, so that's cool and dandy. It's awesome. Also, just of note, once again, this is not the same as dy dx squared, right? They are clearly different, so don't get them confused. They mean different things. And that's cool. We could take the double derivative, but who cares? Why, right? Let's talk a little bit about what we did last time, which was actually finding stationary points with the derivative. So there's another type of stationary point that I didn't go over. We went over maximums and minimums, but there are also these things called points of inflection. All right, we just need to know really what they are and to be aware of them to give us a reason why we're learning the double derivative. Okay, so when we set dy dx equals 0 to find the x values where the stationary points are, it's great. It works for the most part, but it is possible that when I do this, and dy dx equals 0 at a point on the curve, it's possible it might not be a maximum or a minimum. It's this point of inflection thing. So here's an example of that. If I just take y equals x to the third power like this, I take the derivative of that. And I want to see, well, when is my dy dx equal to 0? What are my x values? Well, it turns out that when dy dx is equal to 0, I find that x is equal to 0 right there. And if I look at this point right here, that's not a max or a min. We call that a point of inflection. That's what that guy is. A point of inflection is just a point where the curvature of this curve is changing up. So you see, it's kind of like concave like this, and then all of a sudden it gets more convex, where it's kind of coming towards us like that. So it's changing, we call it changing concavity, but really what's going on is it's just kind of changing the curvature of this guy. All right, aka it's not a max or a minimum, it's a point of inflection. So we kind of have a problem. Our ability to just do dy dx equals 0 and then find what those x values are, it works, but it's got its limitations, which is why the double derivative is so powerful. So actually using the second derivative, I'm just going to give you the rules, and then we're going to go back and see why those rules are the way they are. Okay, and really the second derivative is great to find the nature of a stationary point and determine, is it a maximum or a minimum? And here are the rules of this guy. Okay, so we know normally we set dy dx equal to 0, right? We find those x values where that's true. Cool, we have our points that are either max or min. What I can do with those points is actually plug them in to my double derivative of equation, and depending on what the sign is, that'll tell me right away if it's a max or a min. So if I plug in my x value, let's say it's at 1, where my gradient is 0. If I plug 1 into this, and it turns out it's less than 0, like I have a negative number, then I know that point's a maximum. Likewise, if it's greater than 0 in the double derivative, I know that's a minimum point. Again, we'll talk more about why that is, but I just want you to have the rule and how to apply it. Okay? And this is kind of more of a visual of seeing what's going on. All right? And we'll kind of return to this idea of the derivative being positive and then it changing to negative. And you kind of see why that would be a maximum. We'll talk about this concavity with this guy a little bit, okay? When this doesn't work, though, right, because it sometimes doesn't work, and I'll get into that too, you can still do the same test points to the left and right of the stationary points that we get for x. And we could check their signs with dy dx. Again, that little weird-looking long table that I made you guys, that's something you could still use, although it's just more time-consuming. Okay? So let's actually use the double derivative, and let's see what's going on. All right. So I got this example right here. We have this function right here. And we're going to do three things. Okay, we're going to find the derivative, and likewise the values of x for which dy dx is equal to 0. The second thing we're going to do is we're actually going to take the second derivative, and we're going to plug those x values in that we got in part 1 to see what their nature is, if it's a max or a min. And then finally, part 3, we're actually going to find where those y values are to get those points, because we're only getting the x values right now. So looking at part 1, take the derivative of this guy, again, using my power rule, I get 6x squared plus 6x minus 12. And now I want to see which x values give me stationary points. So I have to set dy dx equal to 0, and I can now solve for x that way. I factor out a 6 out of this guy, and then I factor this inner part out a little bit more, and I can see that I can set x plus 2 equal to 0, x minus 1 equals 0, and I find that x is equal to negative 2 or 1 when dy dx equals 0. So those are the x values of my stationary points. Sweet. Well, part 2 wants me to find the value of the double derivative when I plug these values in for that double derivative. I need to find the double derivative first. So let's do that. I'm just going to take this guy and take the derivative of that, and I'll get 12x plus 6. Then I'm going to plug in each of my x values I got. So when x is equal to negative 2, I'm plugging negative 2 in for x up here. Negative 2 times 12, I'm going to get negative 24 plus 6, I get negative 18. What's most important here is that we notice our double derivative is less than 0, it's smaller. And because it's less than 0, that just tells us right off the bat it's a maximum when x is equal to negative 2. You do the same thing. You could plug x equals 1 into this guy. 12 plus 6 is 18. It's a positive 18. And the double derivative is greater than 0, leading us to the conclusion that it is a minimum. Okay, sweet. So we know that's a max or min. We'll see that on the graph. I'll put it on Desmos so you can see. But the last thing we got to do is actually find the y values of each of these stationary points. And so if I have this x value and this x value, all I'm going to do to find their y values is plug them back in to their original function up here. So when x is equal to negative 2, like I said, I plug negative 2 in for x here, here, and here, and I find that my y value is 20. So at negative 2 comma 20, that's a maximum point. Remember earlier, we said when we plug negative 2 in, we got a maximum out of that guy. Same thing with x equals 1. Plug that guy in, I get y is negative 7, and that is my minimum point right there. So graphically, let's actually take a look at Desmos and see if that's true, if that's the case. So looking at Desmos, here's our function right here, and yeah, we can see negative 2 comma 20 is our maximum. 1 comma negative 7 is our minimum right here. Okay. And so what I kind of want to look at too is why the double derivative is working the way it's working. First of all, I'm going to show the first derivative. I'm going to put that guy up. Okay. Now, it looks like a jumbled mess right now, but let's compare the max and the mins to what's going on with our derivative function. Well, at my max, at x equals negative 2, if I look at negative 2 on my dy dx right here, well, that's when dy dx is 0. That's when my derivative is 0. And so that makes sense. Okay, we solved for it correctly. Same thing right here. I plug in 1 into my derivative function, and I get 0 back for my dy dx. Okay, so that's all good, that's all gravy. But what about if I put my double derivative there? And we have a line right here. Okay. Well, we said at this point and this point, right here we got our max, right here we got our min. Well, right here, if I compare that to -2 on this blue line, well, I see that I get obviously -2 comma -18. That's what happened when we plugged in that x value. And so if I'm looking at that, you could see that it's negative right here, and then as soon as we get about right here, where this occurs, it's going to end up being a positive gradient. So we're taking the gradient of our gradient functions, is really what the double derivative is doing. And as it gets positive, yeah, you're going to see at that point 1 comma -7, or I guess just when x is 1, you see that the double derivative is also positive right there. So going back to those pictures we saw a little bit earlier, right? These are pictures of just normal curves, just normal parabolas, and I can see that, well, if my gradient is positive right here, my dy dx, and this guy is negative over here, it makes sense if I take the double derivative of that and I see that it's less than 0, that means that that thing was decreasing at this point right here. And if you look, it's starting to decrease after that. The slope of it is decreasing. Likewise over here, you notice that, okay, our gradients are going to start getting positive here, so all their values will be positive. They'll be greater than 0 for those gradients right there. So it's a little hard to see with the double derivative, but that's why this rule exists. It has to do with just how the curve is changing, how the slope is changing. And it's changing either positive, it's going more positive, so it started down here at a minimum, and it's getting more negative here, so it started at a maximum right here. And that kind of tells us our critical points right off the bat. Now, one more thing before I go, and this is kind of critical. Sorry about that, we're back. Looking at this guy, the double derivative is really powerful, really makes our job a lot easier. However, it's not perfect. It doesn't work all the time. So for example, if I have this function right here, y equals x to the 4th, I like to call this a fat parabola because it's just a wider parabola. It's really what it is. I take the derivative of that guy. I have dy dx equals 4x cubed. I plug 0 in for dy dx. And I find that, oh, at x equals 0, that is a stationary point. Is it a max or a min? Well, looking at it, I guess it's a min, technically, right? So if I know it's a min, just by looking at it, that means when I plug 0 into my double derivative, well, I should get a positive value out of that. That's not the case here. I take the double derivative of this guy, I get 12x squared, plug 0 into that guy, I get 0 equals 0, but it's not positive or negative. It doesn't tell me anything, and it should actually be a positive number because it's a minimum. My double derivative should be positive, and it's neither. So in this case, we'd probably want to use that first derivative trick. You know, maybe try x equals -1, x equals 1, and just see, oh, hey, what's the sign of that on either side of this stationary point right here? Okay, so we got to be a little careful with double derivatives, but that's how they're used, and that's why they're useful. This is Mr. Knight signing off. Have an excellent day.